Imagine a device that can turn a chemical reaction into electricity, like magic, but with science. That device is called a galvanic cell, also known as a voltaic cell. It converts chemical energy from a spontaneous redox reaction into electrical energy. This means the reaction happens on its own, and we harvest the electrons as electricity. This is how your everyday batteries work. Remote cells, wall clocks, and car batteries all operate on this principle. A galvanic cell consists of two containers called half cells. Each half cell contains a metal electrode immersed in a solution of its own ions. A redox reaction occurs in each half cell. For example, in the famous Daniell cell, one half cell has a zinc rod dipped in zinc sulfate. The other has a copper rod dipped in copper sulfate. In the Daniell cell, the redox reaction happens in two steps. At the anode, zinc metal changes into zinc ions and releases 2 electrons. Zinc solid gives zinc 2 plus aqueous plus 2 electrons. This is oxidation. At the cathode, copper ions take in those 2 electrons and turn into copper metal. Copper 2 plus aqueous plus 2 electrons gives copper solid. This is reduction. This occurs at the cathode. It's reduction. Electrons travel from zinc to copper through an external wire, while ions flow through a salt bridge to maintain charge balance. Let's understand how a Daniell cell is built and how it works. At the anode, zinc metal undergoes oxidation. It loses electrons and changes into zinc 2 plus ions. These electrons collect on the zinc rod, making it negatively charged. At the cathode, copper 2 plus ions in the copper sulfate solution accept these electrons and get reduced to copper metal. This copper metal gets deposited on the copper rod, making it positively charged. The 2 electrodes are connected by a metallic wire on the outside, which allows electrons to flow, and by a salt bridge on the inside, usually a U-shaped tube filled with potassium nitrate. The salt bridge lets ions move so the charge stays balanced. Electrons flow from the anode, zinc, to the cathode, copper. Ions move through the salt bridge to complete the circuit. We can represent the Daniell cell using shorthand notation: zinc solid, single line, zinc 2 plus 1 molar, double line, copper 2 plus 1 molar, single vertical line, copper solid. Single vertical lines show phase boundaries, and double vertical lines represent the salt bridge. Each electrode in a cell has a natural tendency to either lose or gain electrons. This is called its electrode potential. We measure electrode potential by comparing it to the standard hydrogen electrode, which is given a value of 0 volts. For zinc, the standard electrode potential E0 for zinc 2 plus over zinc is minus 0.76 volts. For copper, the standard electrode potential E0 for copper 2 plus over copper is plus 0.34 volts. The overall cell potential, also called the EMF of the cell, is found by subtracting the anode potential from the cathode potential. So, E cell equals 0.34 volts minus 0.76 volts, which equals 1.10 volts. This 1.10 volts is the electrical energy the Daniell cell can produce. The energy produced by a galvanic cell comes from the Gibbs free energy change, delta G, of the redox reaction. We can calculate it using the formula. Delta G naught equals minus NFE naught cell. Here, N is the number of electrons transferred. In the Daniell cell, that's 2. F is Faraday's constant, which is 96,500 coulombs per mole. E naught cell is the standard cell potential, which for the Daniell cell is 1.10 volts. So delta G naught equals minus 2 times 96,500 times 1.10. That gives minus 212,300 joules or minus 212.3 kilojoules. The negative sign tells us the reaction is spontaneous. It happens on its own and produces electrical energy. What does the salt bridge really do? It maintains electrical neutrality in both half cells by allowing ions to move freely but preventing the solutions from mixing. It contains inert electrolytes like potassium chloride or potassium nitrate, which do not react with either of the cell's solutions. Without a salt bridge, the cell would quickly stop working due to charge buildup. To summarize, a galvanic cell uses a redox reaction to generate electricity. It has two half cells, each with its own redox reaction. Electrons flow from anode, oxidation, to cathode, reduction. The salt bridge maintains ion balance. Real-world examples include batteries, fuel cells, and even biological systems. In the next part, we'll explore how to measure electrode potentials and how the standard hydrogen electrode sets the reference for all electrochemical measurements. Are you ready to calibrate your understanding of standard potentials? Let's move ahead.